A universal analog filter is shown here, implemented using 4 ideal op-amps and 2 capacitors and 1 potentiometer with parameter alpha in denominator, and alpha has to be greater than 0. The nice thing is this circuit effectively receives Vin and then generates 4 filtered versions of that. 1 low-pass version, as you can see, 1 high-pass, and bandpass, and then notch filter or stopband version of input comes out just using single circuit. How is this possible? Alright, so to quickly analyze, let's make the assumption that all the op-amps are properly biased, meaning that the positive negative supply voltage is properly connected for all of them, so that we can say op-amps are in linear region of operation, therefore virtual short is valid for all op-amps. By that I mean, since op-amps are in linear region, not saturated with dominant negative feedback, the voltage at the positive input terminal of op-amp is equal to the voltage at negative input terminal of op-amp. So therefore, if we have, let's say, Vx here, then Vx, which is at positive input terminal of op-amp 1, then Vx should appear at the negative input terminal of op-amp 1 as well. So what is that Vx? You can see that we have Vout bandpass, or Vout B, that is connected to the input of the potentiometer. So basically from Vout B to, say, Vx is just a voltage division between these two resistors. That's it. Because for ideal op-amp that is in linear region, no current comes in or goes out of the input terminal. So it's just simple voltage division. So I can write, therefore, Vx is equal to just R2 divided by the voltage division R2 plus 3 over alpha minus 1 times R2. Okay, so these are cancelling out, and as a result, you can see it times, of course, Vout B. So that's bandpass. So you can see that it simply becomes Vx is equal to alpha over 3 times Vout B. Okay, so that's a very simple and nice relationship between Vx and Vout B. So let's refer to it as equation 1. Now, let's write a KCL at this node that we refer to as node Vx, this node, so node X. So I'm going to write a KCL, or Kirchhoff current law, which means that the sum of current arriving at a node should be equal to 0. So KCL at node X indicates that. So there is this current that is going in, so that is, let's say, I1. So I'm going to write it this way, I1. And of course, nothing can go or come out of the input terminal of op-amp, so there is this current I2. So there is this current I2 that is flowing out, let's say, and there is this current I3 that is also flowing out. So this basically this means I1 has to be equal to I2 plus I3. So I1 is equal to I2 plus I3. Let's substitute for these. So what I'm going to get, I1 is simply across R1 is Vin minus Vx. So Vin minus Vx divided by, of course, R1. Now, for I2, I have, as you can see, it goes through this resistor. So it means the voltage across that resistor divided by R1, which is Vx minus Vout low pass. So it's Vx minus Vout low pass divided by R1. Plus, finally for I3, it's across this resistor R1, and it is simply, as you can see, it's simply Vx minus this node, which happened to be, as you can see, high pass. So this is Vout high pass. So it becomes Vx minus Vout high pass divided by still R1. So the nice thing is these R1s cancel out from all sides, and then what we get is simply Vn is equal to 3 times Vx minus Vout low minus Vout high. Now substituting from equation 1 that we just found above, so equation 1 for Vx, then we see that this 3 in denominator is useful because it cancels out this 3, and it gives us Vn is basically equal to alpha times Vout bandpass minus Vout low pass minus Vout high pass. Okay, so this is the beautiful relationship number 2 that I am going to keep here. So Vn, and this is equation number 2 that I need to keep and use. Okay, so this is equation number 2. Now, next step is a very simple step. I'm gonna relate. So this node is, as you can see, V out, bandpass. So I am going to just indicate that. I am going to just say that this node is V out bandpass, and the relationship between V out bandpass and V out high pass is just defined by op-amp number 2, that V out bandpass is its output and V out high pass is its input, and it's just a simple inverting amplifier. So this is inverting amplifier scenario, in which we can simply say V out bandpass for op-amp 2 is equal to minus impedance in feedback path, which is 1 over CS. So minus 1 over CS divided by R, the other impedance, times input, which is V out high. So as a result, we get this interesting outcome that V out bandpass is equal to minus V out high pass divided by RCS. So let's keep this as equation number 3. Okay, last step, we can do the same thing for op-amp 3, in which V out low pass is the output and V out bandpass is the input. So for the same reason, we get V out low pass is equal to minus V out bandpass divided by, for the same reason I just showed you, RCS as well. So this is equation 4. Okay, so I'm going to combine equation 3, 4, and 2. So from 2, applying 3 and 4, basically I'm going to substitute for V out bandpass and V out, say, low pass as well. And all of the things on the right-hand side of equality will be based on V out high pass. So Vn is equal to alpha times V out becomes alpha, so don't forget about negative sign, minus alpha divided by RCS. So that's times V out high pass. So I'm going to factor out negative and V out high pass. And then for negative V out low pass, what I have is, as you can see from equation 4, V out low pass is negative V out bandpass divided by RCS, but then V out bandpass is negative V out high pass over RCS. So effectively I get plus, and there is negative, factor that outside, don't forget about it, 1 over R square, so 1 over R square, CS square, SS square, SS square. And finally, for the last component, I just keep the minus V out, which is plus 1, because negative is factored out, and then times V out high pass. So what is the significance of this? Well, the significance is this outcome. In summary, I can say V out high pass is, if you just take care of simplifying the whole thing, which is the last step, we get minus R square, CS square, SS square, divide by, so divide by, and in denominator we have obviously this outcome. We have 1 plus alpha RCS plus R square CS square plus R square CS square SS square. So the nice thing is, as you can see, and times of course Vn. So this, or basically just V out over H over Vn, is this transfer function basically. So this is the transfer function in S domain. So the nice thing about this, obviously it's a high pass filter, obviously. Reason for that is, as S goes to infinity, then numerator remains what it is, but denominator dominant component is this term, and then as a result, negative r square c square s square divided by r square c square s square approaches 1. So, and as s goes to 0, you can see that denominator remains non-zero, but numerator actually goes to 0. So it doesn't pass DC or low frequency, and it actually, the gain or the transfer function for super high frequency when s goes to infinity is 1, negative 1. So as a result, this is obviously a high-pass filter. And the way it works is, if you form the Bode plot, in which, so magnitude, let's say magnitude Bode plot, you will see that on x-axis we have omega, and on y-axis we have 20 log magnitude, 20 log mag. So in that case, you would see that at S0, we are dead. There is nothing else. Basically, it goes to negative infinity, indicating that it's not letting the DC and low frequency stuff to pass. But then the moment we are past that point, it starts going up with 40 dB per decade. And the moment you hit, let's say, the poles, then if there is a first pole, depending on the value of alpha, that is non-zero in this design, then you start seeing first hitting one pole, and then you start from 40 dB per decade increase, you start going down to, say, 20 dB per decade increase, and finally when you hit the last pole, it goes just to flat. So basically at super high frequency or high enough frequency, the gain is a flat approaching 1 or 0 dB basically. So the gain is approaching, say, 0 dB, and but there might be a scenario in which, if there is a scenario in which the two poles overlap, then of course things would happen faster. But anyways, this is the exact signature look for magnitude Bode plot for high pass filter. Now for the low pass one, remember equation number 3 and 4. So let's start with 3 and 4. So using 3 and 4, and let's say this is equation 5. So 3, 4, 5 combined. We know that basically what we got is V out low is 1 over R2 C2 S2 S squared V out high. That's what we got. So as a result, substituting for this in equation 5, we get basically the transfer function for the low pass output is just 1 over 1 plus alpha RCS plus R square C square S square, which is obviously signature of transfer function of in S domain for low pass filter, because as S goes to infinity, indicating super high enough frequency, then denominator goes to 0. The denominator goes to infinity and the whole thing approaches 0. But then as S goes to 0, indicating low frequency or approaching DC, then this component goes away, this component goes away, and 1 remains, and therefore 1 over 1 will give you gain of unity for DC. So this is obviously a low pass filter. So no wonder it's V out low named. So this is a low pass filter transfer function. Okay, so low pass filter transfer function. Now, for the low pass filter transfer function, obviously the shape of Bode plot looks like this. So the Bode plot for this one, if you form again the same thing, so we have 20 log 10 magnitude of, let's say, h omega. That's the magnitude Bode plot, and x-axis is omega. For this one, we start from 0 dB in dB term, and because when s equal to 0, omega equal to 0, we get 1 over 1, and then 20 log of 1 is 0 dB. And then the moment you hit the first pole, you start going down with 20 dB per decade slope. So this is 20 dB per decade, which means every 10 times increase in frequency, the magnitude goes down by 20 dB. And the moment you hit the second pole, the slope is increased to 40 dB per decade. So 40 dB when you hit the second, let's say, pole in the system, depending on the value of non-zero alpha. Now, this is obviously the expected magnitude Bode plot for a low-pass filter. Okay, so now what's the story about bandpass? So obviously using equation, let's say 3. So now for bandpass, I'm going to just use equation 3 here. So using equation 3 and combine it with equation 5, we know that from 3, bandpass is simply, so V out bandpass is simply 1 over minus 1 over RCS V out high pass. So as a result, we know that now combining with equation 5, substituting, say, for V out high pass and use V out bandpass for it, we get V out bandpass over Vn is equal to negative RCS plus RCS over 1 plus alpha RCS plus R square, CS square, S square. Okay, so this is the transfer function of what is supposed to be the bandpass filtered version. And why is it the case? When S goes to 0, you can see that numerator goes to, so what happens is in this scenario, just to make sure I'm not making a wrong claim, so what happens is as, let's say, S goes to 0, numerator goes to 0, obviously it means DC, near DC or at DC, we don't have, the denominator goes to 0, so it's obviously not passing DC. But denominator remains non-zero. When S goes to infinity, you can see that the dominant term in numerator is RCS, and the dominant term in denominator are R square, CS square. Therefore, the whole thing converges to 1 over RCS when S goes to infinity, which again, at super high frequency or high enough frequency goes nearly to 0. So high frequencies are not passing either. Therefore, only a range of band let's say mid frequencies are passing. Therefore, this is a signature transfer function in S domain for bandpass filter, and effectively it makes sense because what is happening is it is effectively obtained from a cascade of low pass and high pass filter. So for the Bode plot, magnitude Bode plot, it looks exactly as if you are sort of cascading. Let me change the color so that you can see what I'm talking about. So as if you're cascading this Bode plot with this Bode plot with properly designed value of alpha for the potentiometer. So in that sense, it's as if then, for example, the low pass comes in and then your high pass comes in. So there you go. High frequencies are not, in this sort of a very rudimentary shown plot of Bode magnitude plot, high passes stuff are not passing, high frequencies are not passing, low frequencies are not passing, just the mid-range of the frequencies are passing through the filter. Now the last thing is the notch filter. What's happening for notch filter? It's just effectively a summing amplifier. So you can see that here at the bottom of the design, there is just a simple summer or summing amplification. So summing amplifier. So let me just write it this way. So at the very end, we have a summing amplifier, summing inverting amplifier. In which what is happening is the high pass version, so comes in here. So here, as you can see from connection, we have V out high pass. Here, as you can see, it's connected to V out low pass. So V out low pass comes here. So V out low pass comes here. Effectively, the gain of this op-amp 4 is just providing inverting amplification with a gain of R3 over R3 for V out low, and also a negative R3 over R3 for V out high. So, therefore output, which is output of amplifier for op-amp 4, so output V out notch filter or V out N is minus R3 over R3 times V out high, and also minus R3 over R3 for V out low. So effectively, we know that V out notch or bandstop, you can also say bandstop. notch filter is equal to simply just the summation of V out high, V out low. That's it. So effectively you're just adding them up together and there is a negative gain of -1. So what is the meaning of this? Given especially that alpha is always a value, positive value greater than 0, it's as if you are adding the low pass to high pass transfer function or Bode plot. And the way the circuit is designed is in such a way that the overall look of the Bode plot will, for the notch filter, so magnitude Bode plot, or magnitude frequency response in dB terms, will actually look like this. Your low pass will come first. So let me put it this way. So let's say in this scenario, what happens is you have a scheme like this, and then let's put it this way. So that is that is some version of the high pass scheme. That's some version of a low pass scheme, and then after that, some version of a high pass scheme. So effectively, what is happening is we are just adding them together, and of course, because we are adding a high pass and low pass, it's enabling addition of let's say low range frequency or low frequencies or DC, and also addition of high frequencies, but not mid-range frequencies that are filtered out by both the low pass and high pass filter, so they're not showing up at the output of the notch filter. So that's how it is implemented. And if you want to find the transfer function of that, that's not difficult. Let me just change the color so that you can see as the last step. So for V out notch, therefore I'm going to use what I learned from this formula here. Let me make sure I have enough space. So for V out notch, or basically a stop band, I'm going to use this equation. So it is negative the sum of what I found for low pass, and for high pass. So it will be effectively just 1 plus. So I am summing up this one and this one for the low pass and high pass. 1 plus R square, C square, S square, divide by 1 plus alpha RCS plus R square, C square, S square. So that's the, let me just shift so that you can see. That is the response for the notch filter or stop band filter in terms, divide by Vn. That is the transfer function in S domain for the input-output voltage transfer function in S domain for the notch filter or stop band. As you can see, it makes sense. When S goes to infinity, again, you have these dominant terms in numerator denominator, which means it's going to approach gain of -1. When S goes to 0, which means you're dealing with DC, everything goes away except these two ones in numerator denominator. So again, you're approaching gain of -1. At mid frequency, there is a frequency when numerator becomes 0, which is 1 plus R square, C square, S square. So if you set it to 0, I'm talking about S equal to plus minus, let's say J over 1 over RCJ. So it's something like this. So at a specific frequencies, then you hit zeroing exactly the numerator, so therefore it will act as a notch filter around those frequencies. All right, I hope that this example of a nice, simple approach to design of the universal analog filter to realize 4 different types of filter using same circuit is helpful, that also include the feedback in this system. The feedback is the part that deals with the potentiometer 3 over alpha minus 1. So I hope that this is helpful in terms of showing how this can be designed and analyzed. Thanks. Thank you for watching.